Thank you. And so it's a great pleasure to, as I was thinking, sort of undergoing Poincare recurrence, coming back for a strings in Beijing again after 10 years. Of course, it's not really a recurrence because it's been really inspiring to see all the changes in Chinese science and Chinese string theory in the last 10 years. So it's been very nice to be back. And I'd like to thank the organizers for inviting me to speak. So this is work that will hopefully appear soon, done with several of these people. And I would particularly like to highlight the two of the younger people there, Apratim Kaviraj and Kallol Sen, who are students of Ananda Sinha and who have been fantastic contributors in this work. Thanks to Slava and friends, we've had a successful revival of the conformal bootstrap program in recent years. And, So what I'll describe here is, in a sense, a new approach, but actually in some ways an old approach to this program. What we will see is that this is calculationally fairly effective. It appears to be quite effective in that it can reproduce most existing analytical results and, in fact, go beyond for operator dimensions and OP coefficients. In particular, I'll illustrate it in two contexts: the canonical 4 minus epsilon expansion for the Wilson-Fisher fixed point, and another distinct limit, a large spin limit, something valid in any dimension. So this will, of course, be something that'll be the mainstay of my talk to illustrate this. But there is also, I feel this approach is conceptually very suggestive. And I won't say very much about this, but I'll just restrict to mentioning that, as you will see, there's a sort of a dual ADS type description, which, so I'll leave the suggestiveness to suggest various things to you. And I won't say very much more about this, but we can discuss later. So this approach relies on two ingredients. The first is very retro. I mean, it goes back a long way to the original approach of Polyakov, and more than 40 years ago. But now we'll revive it in a modern incarnation. So Polyakov's philosophy was to use it is not much appreciated that Polyakov's philosophy was somewhat different from what we understand by bootstrap nowadays. He actually he proposed that we use a different set of blocks, and we'll see that there are actually things that are built from sort of Witten diagrams in ADS. So instead of conformal blocks, and it's this fact that it's sort of related to ADS that's the conceptually suggestive part of it. But of course, it was very difficult to make this approach work. And so the critical ingredient to make it calculationally effective is to implement it in melon space, a technology that we've seen in the last several years being developed. And melon space is very nice because it has properties like meromorphy, and there's an analogy to scattering amplitudes in momentum space and so on, which we will exploit. So these are the two main ingredients that will go into the talk. Let me just offer you a sort of a sampling of results. Sorry for these blobs. I couldn't get my keynote working properly. But the first context of the epsilon expansion and the 4 minus epsilon expansion, we can reproduce the dimensions of various operators. These are things that were computed using Feynman diagrams going back to Wilson and Kogut. And as you can see, reproducing fairly non-trivial corrections. These are things that are computed by higher order Feynman diagrams. So this is something one can see easily. Moreover, one can look at the anomalous dimensions of the bilinears, the twist 2 currents. So the Wilson and Kogut had the leading correction, and this is the thing that vanishes at L equal to 2, we can find the next order correction. It looks quite horrendous, but it surprisingly vanishes at L equal to 2. But most gratifying, I think, is the fact that we can compute OPE coefficients, which are very difficult to compute using Feynman diagram analysis. So for instance, the 3-point function of 2 phi's and the phi square operator is something, of course, the leading correction you can compute using Feynman diagrams, but the next correction is not easy, and it's something we can find fairly easily. In fact, we can find the OPE coefficients of phi with any higher spin L current, and it takes on the order epsilon square correction is quite is reasonably simple. These h's are harmonic numbers. The order epsilon cube is, we have an explicit expression. It's quite hairy, but I'll just flash various numbers. You can compute it for any spin that you want. So that's the epsilon expansion. There's the large spin limit, which is something that has been studied in the last couple of years in the context of the analytic bootstrap. There are sort of two different domains that people have studied. There's the so-called large twist gap or strong coupling regime, in which you have a minimal twist operator. So people using the light cone expansion argued that the anomalous dimensions for twist 2 currents is given by an explicit formula like this, and also its OPE coefficient. This is something we can see as well. There's an opposite regime, which Zhibodev talked about in last year's strings meeting in Bangalore. There you have, again, an expansion for the anomalous dimensions. There's a sort of a expansion in terms of logarithms. But those methods were unable to fix these coefficients. And here one can fix the coefficients in terms of the dimensions in a fairly explicit way. And moreover, there are cross-checks between these. There are overlapping regimes. There are checks with large n and so on. So the new things pass these consistency checks. So OK, so that's an idea of the results. So let me explain what the idea is, the philosophy, following the philosophy of Polyakov. So if you take a 4-point function, let's say of identical scalars for simplicity, the idea is to expand it in a basis, in a new basis, in a sense. These will be the ones that will be built from the Witten diagrams. What we demand of these new building blocks is that they satisfy conformal invariance, which is, of course, always good. But they should be also consistent with unitarity in that they factorize on physical operators with the right residues. And the last requirement, which is not something we normally do, which is that we demand it be crossing symmetric, and we do that by summing over all the channels. So this is sort of by construction crossing symmetric. This is constructed so that you sum over all the ST and U channels. So what happens is that now you're not guaranteed that the expansion will be consistent with an operator product expansion when you expand in any given channel. So what I mean by that is that there will be generally spurious powers. There will be spurious powers. Spurious powers are in one of the cross ratios, and in the case of identical scalars, also logarithmic terms. And now what Polyakov demanded was that these terms cancel, and those give constraints on operator dimensions and OPE coefficients. I just want to emphasize that this log term does not come from any anomalous dimension, unlike what one sees in ADS CFT. The contrast with the conventional bootstrap is that there, of course, we expand in terms of conformal blocks, which are, by construction, conformally invariant. They're consistent with unitarity. They factorize with the right residues. and they are, the consistency with the OPE is guaranteed because, at least in any given channel, you sum over all the physical operators in that channel, and that guarantees the consistency. But of course, now what's not guaranteed is that the answer is channel symmetric, and so the associativity of the OPE is not guaranteed, and it's that demanding that which gives non-trivial constraints on operator dimensions. So this is the more conventional philosophy, but we will be adopting the older one. So these building blocks, as I was saying, are essentially exchange-written diagrams, and the reason to work with them is, firstly, as will be clearer a little later, they are better behaved compared to conformal blocks. So the exchange-written diagrams are the conventional ones in which they're labeled by the spin and the dimension of the exchanged operator. We're taking these to be all identical scalars right now. It's a function of the cross ratios. And similarly, you can write the other two diagrams as well. So these will be our building blocks. And these building blocks satisfy our criteria. They're conformally invariant. They obey factorization. They come from a field theory, and they obey factorization, and this will be manifest in Mellin space. And by construction, they're crossing invariant because you're summing over all three of them. However, in position space, these diagrams are complicated, as anyone who has worked with them can testify. So it'll be easier to deal with them in Mellin space, and in particular properties like factorization as well as the asymptotic behavior will be more transparent in Mellin space. So let's migrate to Mellin space. This is how a Mellin amplitude would look like for a 4-point function. It's essentially a Mellin transform in the cross ratios. Again, we are taking identical external scalars. It's a Mellin transform in the cross ratios together with some convenient measure factors. The conformal blocks, of course, will translate to something in Mellin space. We'll denote them by B. In fact, these are very explicitly known in the literature. They are built from certain polynomials in the S and T variables, the Mellin variables, of degree L, where L is the spin. There are some bunch of gamma factors. And there's, importantly, a projector. This is a projector which sort of cancels out so-called shadow pole, which I don't have time to explain. But essentially, this factor leads to an exponential behavior at large S for these conformal blocks. These, as I said, they factorize on poles. So these are meromorphic quantity. Well, they're entire functions, but they factorize on a series of poles in delta, for instance. And the residues are the 3-point functions. In fact, there's a whole series of descendant poles, so on. So what about the blocks that we are now considering built from Witten diagrams? There's some ambiguity in the choice of these building blocks, but it's known that it's known that the meromorphic part of the conformal block coincides with the Mellin version of these Witten diagrams. So they have exactly this meromorphic part. And in fact, you can choose that to be the Witten diagram in Mellin space. You could add a polynomial to this, but that's an ambiguity which is potentially useful, but we won't make use of it right now. So the good thing about this is that there's no exponentially growing behavior at infinity. These are polynomially bounded. These are polynomials in T of degree L. If you want to see how these look, for the simplest case of a scalar, I've written it for you. I wrote the conformal blocks in the last slide for general spin. You can specialize that to spin equal to 0, take the meromorphic part, and it sums up to a hypergeometric function like this. So it's a very well-defined, nice object. So as I said, we'll sum over all the S, T, and U channels and get a crossing symmetric amplitude. In position space, the requirement was the cancellation of spurious poles of this kind. In Mellin space, that requirement translates into canceling spurious single and double poles, because the whole amplitude, including the measure, will have a piece which will go like this, and a piece which will go like this in terms of the dimension of the external scalar, delta phi. There'll be additional pieces corresponding to the actual physical pole. There'll be descendant poles, and so on. But this is the piece that we'll focus on. Now the condition to cancel these spurious poles is a nice condition in Mellin space. It's basically that the net residue vanishes as a function of t. So these are functions of t, the other variable, and you demand that they identically vanish as a function of t. What makes this easy to implement is that there's a very natural decomposition of these residues in terms of a basis of partial wave. What are the analogs of partial waves? These are certain class of orthogonal polynomials, which are specializations of the Mach polynomial. So you can decompose the total residue in terms of these polynomials. It'll have contributions from the ST and U channels. And we can demand that the coefficient of each of these polynomials for each L vanishes. So you get an infinite number of constraints from an equation like this. You sum over all the dimensions, but this is true for all L. So I'll just inflict a couple of technicalities on you, just so that you get some appreciation of what it involves. So it's useful to use a so-called spectral representation of these. For a general case, it's useful to use the spectral representation, which is something that people have studied in the literature, a spectral representation for this Witten diagram building block. It's built in terms of the Mach polynomials, some gamma factors, and a spectral weight. The spectral weight shows that there are poles at the physical operator, but there are other poles as well. This arises from writing bulk-to-bulk propagators of Witten exchange diagrams in terms of products of bulk-to-boundary propagators. And the spectral weight, as I said, exhibits poles at operators, as well as the double trace contribution, which gives rise to the spurious poles. And this is useful for picking out these specific contributions that I said correspond to the double poles and the single poles. The nice thing, again, which helps, is that at these poles, the residue simplifies. The Mach polynomials reduce to these polynomials that I was alluding to earlier. These are a nice set of orthogonal polynomials known in the mathematics literature as continuous Hahn polynomials. They can be written explicitly in terms of some hypergeometric functions. So you can now try to, so I've been talking, let's say we are in the S channel. We can try to pick out these residues. And the nice simplification when writing in terms of this basis of partial wave polynomials is that you can explicitly work out the coefficients for each L. And the important thing is that in the S channel, the contribution to the spurious poles for a definite L contributes only to that polynomial of degree L. So it's just a simple piece which you can extract down explicitly. It's a little more complicated in the T and U channels to add in to isolate the spurious poles, because a fixed spin in the T channel gets contributions from all L. If you decompose it into these orthogonal polynomials, it gets contributions from all L for a fixed L prime. But you can use the orthogonality property of these polynomials to pick up those contributions, and you can work out the pole pieces, the double pole pieces. The identity piece, it's convenient to sort of separately work with that. The other nice thing, because of the properties of all these polynomials, is that the U channel gives an identical contribution to the T channel. So you just have to add twice the U channel contribution, the T channel contribution, to the earlier S channel contribution that I had, and you get constraint equations like this for all spin L, and for each of these I equal to 1 to 2 for the single pole and the double pole. So we can implement this in the epsilon expansion as an alternative to Feynman diagrams. So the important thing is to exploit that the stress tensor has protected dimensions. So you look at the L equal to 2 channel in the S channel, the spin 2 exchange. To leading order, only the S channel contributes, and that fixes some of the leading corrections to the dimension and the OPE coefficients. By the way, it's nice that the 2 poles, one of them typically fixes the dimension, the other one fixes the OPE coefficients. You can then go back and include the T channel and sort of iterate. And in fact, due to certain miraculous sort of cancellations in the T channel, you don't have an infinite number of operators contributing, but only the phi square to low orders, which is what we've been able to compute, and which is what gives you these results that I flashed earlier. These are, of course, known results, but it's heartening to obtain them. And it was quite surprising that these funny denominators all came. And as I said, you can go ahead and compute the anomalous dimensions of the twist 2 operators. You get this epsilon cube term, and this is it's written in terms of these harmonic numbers. You can get the next correction to the OPE coefficient of the phi with 2 phi's and phi square. And I think most surprisingly to us, all the OPE coefficients, these are actually the squares of the OPE coefficients for the 2 phi's with the spin L current. And as I said, this is the epsilon square, which we can write explicitly. This one is lots of horrendous rational numbers. The other context, as I mentioned, was that of the higher spins in the larger L limit. So this is something using the light cone and double light cone expansion people have been studying in the last few years. In this approach that I sketched for you, what's nice about the large spin limit is that these orthogonal polynomials simplify, and you can sort of do, you can simplify the T channel, which was the more complicated channel, and you can reproduce when in the strong coupling case where there's a sort of a single minimal twist operator, you can reproduce this in terms of the minimal twist. This tau is the minimal twist. L is the spin of the minimal twist operator in terms of the OPE coefficients and so on. These results were obtained by some of these people, as well as the OPE coefficients. But you can look in the opposite limit, where you might, like a weak coupling limit in which there's a perturbative parameter, but now there's no single minimal twist operator, in which case, as we heard last year from Zhibodev of the work with Alde, you can write down this sort of expansion in powers of logs, but they're each multiplied by function of the perturbative parameter g. Now, this is a perturbative expansion because each of these begins with g to the appropriate power, the log, so that this condition is sort of satisfied. But the double light cone techniques don't really fix these coefficients for you. But here you see that you can explicitly write them in terms of the dimensions. These are the corrections to the dimensions, the phi and phi square fields. You can write an explicit form for them. And you can, in fact, check these with the epsilon expansion results that I showed earlier, where there's an overlapping regime, because this is for large spin, and that's for epsilon, and there's an overlapping regime. So we can try to, in fact, combine the results of these two expansions. And of course, the benchmark these days is the numerical results on the 3D Ising model. And so you can try to compare with them. So of course, we haven't the epsilon expansion already for the basic fields, the spin field and the energy field. We haven't improved on those dimensions since our epsilon expansion has reproduced them, but not gone beyond them. But for the spin fields, in fact, we now can match with the we can, this is with the epsilon expansion, and this is like a spin 4 field. So the numerical values are very close. Now the deviation is sort of 0.02%. But most interestingly is the fact that the OPE coefficients, for instance, the central charge is, of course, a very important one. This is related to the central charge is related to the OPE coefficient by what identities, the OPE coefficient of the spin 2. And now with our results for the spin 2 OPE coefficients, you get one higher order in epsilon and reproduces the already existing calculation in the epsilon expansion. And this makes the match of CT with the numerics now up to 1%. So I'm at my end. So if you're wondering whether this method can be applied to your favorite CFT, the answer is in principle yes, but probably in practice to extract out results will require more refinements and extensions. I'll just mention some of them which are on our list. So non-identical scalars is very easy. It's just a straightforward generalization. Non-identical external scalars. To put in spinning external operators should not be very much more difficult. I think much of the machinery has already been developed. It's again straightforward to generalize to n-component scalars. We heard in Igor and Sergei's talk interesting conjectures, statements about Gross-Neveu-like theories, 3D QED, and so on. And perhaps one could access them once one sort of solves these, generalizes these. I should say that we took the simplest constraints from our from the leading order pole. It's possible that there are more constraints from descendants poles, and this would hopefully we should be able to make this a systematic procedure for solving the constraint equations. And of course, there's probably only so much one can go analytically, and but we are hopeful that this will be a useful approach for numerical implementation as well. And finally, we've taken some baby steps for about properties of CFTs in higher than 4 dimensions, but it's still preliminary. Okay, thank you very much. Sheshe.
Rajesh, amazing progress. Congratulations.
Thanks.
In Poliakov's paper, it was totally unclear why his assumption that only 5-squared operator contributes.
Yes,
justified. So you said
this can be justified here. We can see exactly at which order. So that's why we were sort of limited to the order in epsilon that I showed you. You can show that basically. The details will be there in our paper, but basically there are some cancellations at leading order between the contributions from higher spin operators because they start with some higher order in epsilon and so on. So it's a little bit delicate, but one can see very explicitly where to what order you can trust this and so on. So yeah, because there are explicit expressions for the OPE coefficients and so on, so you can do that. But I can tell you more in detail privately.
Okay, there's one question over there. Do you get any simplification if you assume that all the higher spin operators have large conformal dimensions?
Yeah, yeah, I would. We haven't seriously explored that, but I would imagine there is a small parameter which is 1 over the coupling and or the large dimensions, whatever. And I think there should be simplifications, but we have not yet seriously explored that. Thanks.